How one U.S. engineer's crazy supercharger mod made Mustangs Outclimb Zeros in 60 seconds. The P-51 Mustang was obsolete before it ever fired a shot. Built around an engine that choked above 15,000 feet, it entered service as a low-altitude reconnaissance plane while German fighters ruled the European sky at 25,000. Yet within 18 months, the same airframe, fitted with a British engine modification American engineers initially dismissed as impractical, became the fighter that won air supremacy over both Europe and Japan. Before we go deeper into how this decision changed the Pacific War forever, make sure to subscribe for more history that actually happened. The transformation defied every assumption about aircraft development. In 1942, the North American P-51 Mustang represented advanced aerodynamics paired with inadequate power. Its laminar flow wing design reduced drag better than any contemporary fighter. Its internal fuel capacity exceeded 180 gallons. But the Allison V1710 engine, reliable and powerful at sea level, lost critical horsepower as altitude increased, making the aircraft useless for the high-altitude bomber escort missions the Army Air Forces desperately needed. The solution came not from Detroit engineering labs or Wright field test programs, but from a single test pilot's 30-minute flight over the English countryside and his radical suggestion: rip out the American engine and install a British Rolls-Royce Merlin with a two-stage supercharger. The modification seemed impossible. Different mounting points. Different propeller rotation. Different cooling requirements. Yet when the hybrid fighter flew in October 1942, it climbed 50% faster than the original and added 8,000 feet to its service ceiling. More critically, the two-stage supercharger maintained manifold pressure at altitudes where Allison-powered Mustangs wheezed and stalled. The numbers told a story that would reshape aerial combat. At 25,000 feet, a Merlin Mustang could outrun, outclimb, and outfight anything flying for the Axis powers. By late 1944, P-51DS escorted B-29 Superfortresses from Iwo Jima to Tokyo, a 1,500-mile round-trip no other single-engine fighter could accomplish. The aircraft that had been relegated to photo reconnaissance was now the long-range escort that made strategic bombing viable and gave American pilots the high-altitude performance to challenge Japanese fighters that had owned the Pacific sky since Pearl Harbor. The path to this transformation began not with American ambition but British desperation. In April 1940, the British Purchasing Commission approached North American Aviation with an urgent request: build Curtiss P-40 fighters under license to supplement Royal Air Force strength after France fell. North American President James Dutch Kindleberger countered with an audacious proposal. His engineers, led by chief designer Edgar Schmude and project engineer Raymond Rice, could design and build a completely new fighter in 120 days, faster and better than the P-40. The British, skeptical but desperate, agreed. The prototype NA-73X flew on October 26, 1940, powered by an Allison VE-1710-39 engine producing 1,150 horsepower at takeoff. The aircraft incorporated innovations that would define American fighter design for a decade. Schmude, an Austrian immigrant who had worked for Fokker and Messerschmitt before joining North American, understood boundary layer theory better than most aerodynamicists. The Mustang's wing used laminar flow airfoils that delayed air turbulence over the surface, dramatically reducing parasitic drag. The radiator installation beneath the fuselage created the Meredith effect, recovering thrust from heated cooling air expelled rearward. These refinements gave the P-51 a top speed of 382 miles per hour at 13,000 feet using an engine that produced less power than contemporary fighters. But speed at low altitude meant nothing if the aircraft could not fight where combat occurred. The Allison VE-1710 engine was a masterpiece of American engineering in its intended role. A 1,710 cubic inch liquid-cooled VE-12, it produced reliable power for low-altitude operations and powered the PA-38 Lightning and PA-40 Warhawk successfully. The engine's single-stage, single-speed supercharger compressed intake air using a centrifugal impeller driven directly from the crankshaft at a fixed ratio. This design worked beautifully at altitudes below 12,000 feet, where ambient air pressure remained high enough that compression maintained proper fuel-air mixture density. But as the aircraft climbed, atmospheric pressure dropped exponentially. At 20,000 feet, air pressure falls to roughly half its sea level value. The single-stage supercharger could not compress the thin air sufficiently to maintain manifold pressure, and engine power dropped proportionally. At 25,000 feet, where Luftwaffe fighters routinely operated, an Allison VE 1710 lost 40% of its rated horsepower. For bomber escort missions over Europe, this limitation was catastrophic. German Focke-Wulf FW-190s and Messerschmitt Bf-109GS operated comfortably at 25,000 to 30,000 feet, attacking B-17 formations from above, while American escorts struggled in oxygen-starved climbs that left them vulnerable and ineffective. The Royal Air Force recognized this problem immediately. Initial combat trials with Allison-powered Mustang in 1942 confirmed the aircraft's excellent low-altitude performance but dismal high-altitude capabilities. RAF squadrons used the type for ground attack and tactical reconnaissance, roles where speed and range at 10,000 feet mattered more than climb rate or service ceiling. But the aircraft's potential remained unfulfilled. The airframe was too good to waste on secondary missions. The solution came from an unexpected source: Ronald Harker, chief test pilot for Rolls-Royce at their Hucknall facility. In April 1942, Harker flew a Mustang I on loan from the RAF for evaluation. The 30-minute test flight convinced him that the aircraft's superb handling and efficient design were being wasted on an inadequate power plant. He wrote in his report that the Mustang combined with a Merlin engine would create a fighter superior to anything currently flying. The recommendation faced institutional resistance from multiple directions. The Air Ministry viewed Merlin production as too critical for Spitfire and Lancaster programs to divert engines to an American fighter. North American aviation worried about redesigning engine mounts, cooling systems, and control interfaces. The U.S. Army Air Forces preferred supporting American manufacturers over British dependencies. But combat losses were mounting, and the strategic bombing campaign desperately needed long-range escort fighters that could protect B-17s and B-24s deep into Germany. Rolls-Royce proceeded with private venture modifications in June 1942, converting 5 Mustangs to accept Merlin 61 engines. The Merlin 61 represented the culmination of years of British supercharger development. It featured a 2-stage, 2-speed mechanical supercharger system fundamentally different from the single-stage Allison design. The first supercharger stage, driven through a 2-speed gearbox, compressed incoming air and fed it through an intercooler, a radiator that cooled the compressed air before it entered the second stage. The second stage compressed the air further before it entered the engine's intake manifold. This 2-stage compression achieved manifold pressures impossible for single-stage designs, maintaining power output at altitudes exceeding 30,000 feet. The engineering principle behind 2-stage supercharging addresses the fundamental thermodynamic limitation of compressing gases. When air is compressed, its temperature increases according to the ideal gas law. Hotter air is less dense, reducing the oxygen available for combustion and limiting power gains from increased pressure. A single large compressor must work harder and generates more heat, ultimately self-limiting its effectiveness. But 2 smaller compressors working in series, with intercooling between stages, can achieve higher overall compression ratios with less temperature increase. The Merlin 61's first stage compressed intake air to approximately 12 pounds per square inch absolute. The intercooler cooled this compressed air from roughly 200 degrees Fahrenheit to 100 degrees Fahrenheit before the second stage compressed it further to over 18 psi at maximum boost. This cooled, compressed air entered the engine with oxygen density approaching sea level conditions even at 25,000 feet altitude, allowing the engine to produce 1,565 horsepower, more power at 20,000 feet than the Allison produced at sea level. The first Merlin Mustang hybrid flew on October 13, 1942, from Hucknall. Test pilot Ron Shepard advanced the throttle and felt the aircraft accelerate differently than any Mustang had before. The Merlin's deeper exhaust note accompanied smooth, powerful thrust that did not fade as altitude increased. Climb rate to 20,000 feet improved from nearly 9 minutes to under 6. Top speed at 25,000 feet increased from 390 miles per hour to 433 miles per hour. Service ceiling rose from 31,000 feet to 41,900 feet. The combination of superior aerodynamics and adequate high-altitude power transformed the P-51 from a specialized ground attack aircraft into a fighter capable of dominating any opponent at any altitude. But converting the modification from experimental prototype to production fighter required convincing American manufacturers and military procurement officials that the added complexity, cost, and dependency on British licensing were worthwhile. North American aviation had already begun exploring Merlin installation independently. In July 1942, even before the British conversion flew, the company received 2 Packard-built Merlin engines under a licensing agreement between Rolls-Royce and Packard Motor Car Company. Packard had been building Merlins for British bombers since 1941, producing the VE 1650-1 version equivalent to the Merlin XX. But the 2-stage Merlin 61 variants required different tooling and represented a significant engineering challenge for mass production. The Packard VE 1650-3, American equivalent to the Merlin 66, entered production in late 1942. The engine displaced 1,649 cubic inches through a 60-degree V12 configuration with bore and stroke of 5.4 inches by 6 inches. Compression ratio was 6:1, conservative by modern standards but necessary for the 100-octane fuel available in quantity during wartime. The 2-stage supercharger assembly added complexity and weight. The first stage impeller measured 12 inches in diameter, the second stage was 10.1 inches. The 2-speed drive system allowed the pilot to select low gear for altitudes below 19,000 feet and high gear above, optimizing supercharger efficiency across the aircraft's operational envelope. An automatic boost control system adjusted throttle position to maintain safe manifold pressure, preventing overboost conditions that could destroy the engine. The intercooler, mounted alongside the oil cooler beneath the fuselage, used ethylene glycol coolant to remove heat from compressed air between supercharger stages. This cooling system added weight and complexity but was essential for extracting maximum power at altitude. The complete Packard VE 1650-3 weighed 1,640 pounds dry, roughly 100 pounds more than the Allison it replaced, but the weight penalty was negligible compared to performance gains. Integrating the Merlin into the Mustang airframe required solving multiple engineering challenges. The Merlin rotated counterclockwise when viewed from the pilot's seat, opposite to the Allison's clockwise rotation. This difference affected propeller selection, engine mount design, and even the rudder trim required for coordinated flight. North American engineers designed new engine mounts that positioned the Merlin's thrust line correctly and accommodated the different bolt patterns on the British engine. The cooling system required enlarging the ventral radiator intake to handle increased heat rejection from both the larger engine and the intercooler system. The propeller, now turning in the opposite direction, required recalibrating the constant speed governor and adjusting the pitch control linkage. The exhaust system changed completely. While the Allison used individual exhaust stacks that protruded from the cowling sides, the Merlin installation featured multiple exhaust stacks on each side that not only expelled combustion gases but also generated measurable thrust through careful shaping of the outlet nozzles. These stacks were tuned to create negative pressure pulses that aided cylinder scavenging, improving volumetric efficiency. Every detail mattered when converting an aircraft designed for one power plant to accept another. Even seemingly minor changes like moving the engine-driven hydraulic pump required rerouting lines, recalibrating pressures, and ensuring that landing gear and flap systems operated correctly with different flow characteristics. The first American-built P-51B flew on November 30, 1942, less than 2 months after the British prototype. The designation change from A to B reflected the new engine and associated modifications. Flight testing at Wright Field confirmed performance that exceeded expectations. At military power, the P-51B achieved 441 miles per hour at 29,800 feet. Rate of climb at sea level reached 3,475 feet per minute. Combat radius with internal fuel extended to 475 miles, and with drop tanks, escort missions covering 1,300 miles became feasible. These numbers represented more than incremental improvement, they constituted a fundamental shift in what single-engine fighters could accomplish. But numbers on test forms did not win wars. The aircraft needed to prove itself in combat, and that proof came over Europe in the Winter of 1943. The 354th Fighter Group, equipped with P-51BS, arrived in England in October 1943 and flew their first combat mission on December 1, escorting B-17s to a target near Amiens, France. The mission demonstrated immediately what the new fighter could accomplish. Unlike P-47 Thunderbolts, which could escort bombers partway into Germany before fuel constraints forced them to turn back, the Mustangs accompanied the bombers to the target, fought off Luftwaffe interceptors, and returned to England with fuel to spare. Pilots reported that the P-51B could outturn Focke-Wulf 190s, outdive Messerschmitt 109s, and sustain high-speed combat at altitudes where previous American escorts struggled. The first large-scale test came on March 4, 1944, when 8th Air Force mounted its first major raid against Berlin. Over 660 heavy bombers, escorted by P-51BS and P-51CS, struck targets in the German capital. Luftwaffe fighters rose to defend, and the resulting air battle vindicated the Mustang's design. American pilots claimed 82 German aircraft destroyed for the loss of 11 P-51s. The ability to escort bombers all the way to Berlin and back, engaging enemy fighters over the target and during withdrawal, changed the strategic bombing campaign fundamentally. German fighters could no longer attack American bomber formations with impunity during the final approach to targets deep in Germany. The long-range escort capability that had been theoretically impossible in 1942 was now operational reality. But the P-51B, excellent as it was, suffered from operational limitations that combat quickly revealed. The canopy, a Malcolm hood with heavy framing, restricted visibility during combat maneuvering. Pilots complained that they could not see above and behind adequately, leaving them vulnerable to attacks from the 6 o'clock high position. The 4.50 caliber machine guns, while reliable, lacked the weight of fire needed to destroy German bombers quickly. Ammunition capacity of 350 rounds per gun for the inboard weapons and 280 rounds for the outboard guns limited sustained combat. And most critically, the gun suffered from jamming problems when pilots executed high-G maneuvers, rendering the aircraft defenseless during violent combat. North American addressed these deficiencies in the P-51D model, which entered production in spring 1944. The most visible change was the bubble canopy, a clear teardrop-shaped enclosure that provided 360-degree visibility. British pilots had demonstrated bubble canopy advantages on Spitfires and Typhoons. North American adapted the concept for the Mustang, cutting down the fuselage behind the cockpit and installing a Malcolm or later a purpose-designed canopy that gave the pilot unobstructed views in all directions. Armament increased to 6.50 caliber Browning M2 machine guns, 3 in each wing, with 400 rounds per inboard gun and 270 rounds per outboard weapon. The total ammunition load increased to 1,880 rounds, providing roughly 25 seconds of sustained fire. More importantly, the gun installation eliminated the jamming problems through improved ammunition feed chutes and stronger mounting hardware that resisted deflection during high-G loads. The P-51D also incorporated K-14 gunsight technology, a gyroscopic computing sight that automatically calculated lead angles for deflection shooting. Previous reflector sights required pilots to estimate lead based on experience and intuition. The K-14 used a gyroscope to sense aircraft motion and mechanically computed the proper aim point, projecting it onto a combining glass in front of the pilot. This technology, derived from British developments, significantly improved hit probability, especially for novice pilots who had not developed the intuitive feel for deflection shooting that came from hundreds of combat hours. By mid-1944, P-51D production reached 400 aircraft per month. The Inglewood, California plant and a new facility in Dallas, Texas worked multiple shifts to meet demand. Every aircraft that rolled off the assembly line received the Packard VE 1650-7 engine, the final refinement of the two-stage Merlin design optimized for high-altitude performance. This engine produced 1,695 horsepower at military power and 1,790 horsepower at war emergency power, achieved by injecting a water-methanol mixture into the supercharger to reduce intake temperature and suppress detonation. The system allowed brief bursts of power exceeding the engine's continuous rating, critical during combat emergencies when absolute performance meant survival. The modification's true test came not over Europe but in the Pacific, where the strategic situation and enemy capabilities differed fundamentally from the European theater. Japanese fighter doctrine emphasized maneuverability and climb rate at the expense of protection and firepower. The Mitsubishi A6M0, though obsolescent by 1944, remained formidable in the hands of experienced pilots. It could outturn any American fighter at low speeds and climb rapidly through medium altitudes. Early war American fighters, P-40s, F-4F Wildcats, even F-6F Hellcats, countered the Zero's advantages through superior diving speed and structural strength, using boom and zoom tactics that avoided turning dogfights. But these tactics worked only when American pilots maintained energy advantage through disciplined flying. The P-51, with its combination of speed, climb rate, and reasonable turning ability, offered American pilots the option of engaging Zeros on more equal terms without giving up the high-altitude performance and range needed for long-distance escort missions. The Pacific presented unique operational challenges that tested the Mustang's capabilities to their limits. Distances between bases and targets exceeded anything seen in Europe. From Iwo Jima to Tokyo was 660 nautical miles one way, requiring over 3 hours of flight time each direction. Early warning systems were primitive or non-existent, meaning fighters had to remain airborne on combat air patrol for hours. Weather over the Pacific could change without warning, and navigation over featureless ocean demanded precision that European operations rarely required. The P-51's internal fuel capacity of 269 gallons plus two 110-gallon drop tanks gave it the endurance needed for these missions, but barely. Pilots had to manage fuel consumption meticulously, leaning mixtures to extend range while maintaining enough reserve for combat and the return flight. The first P-51s reached the Pacific theater in late 1944, initially operating from bases in China and the Philippines. But their strategic impact came in spring 1945 when the 7th Fighter Command deployed 3 fighter groups equipped with P-51DS to Iwo Jima, the volcanic island captured at terrible cost specifically to provide an emergency landing field for damaged B-29s and a base for escort fighters. On April 7, 1945, 108 P-51DS took off from Iwo Jima's North Field on the first very long-range escort mission to Japan. The flight plan called for 7 hours of flying time, 3 hours to the Japanese coast, 1 hour over the target area escorting B-29s attacking the Nakajima aircraft plant at Musashino, and 3 hours return. Total distance exceeded 1,500 statute miles, longer than any fighter escort mission previously attempted. Weather complicated navigation, with cloud cover obscuring visual checkpoints and forcing pilots to rely on dead reckoning and radio compass bearings. Japanese fighters rose to intercept over Tokyo, and the resulting combat demonstrated what the Merlin engine modification had achieved. P-51DS climbed through 20,000 feet with power to spare, engaging Ki-43 Oscars and Ki-44 Tojos that had been optimized for medium-altitude combat. The American fighters' superior high-altitude performance allowed them to maintain energy advantage, dictating engagement terms and breaking off when necessary without being caught in turning fights where Japanese maneuverability could be decisive. The comparison between P-51D and A6M0 performance specifications illustrates why engine technology mattered more than airframe design. The Zero's Nakajima Seiki radial engine produced 1,130 horsepower at takeoff but lacked effective supercharging for high-altitude operations. At 20,000 feet, power dropped to roughly 850 horsepower. The aircraft could climb rapidly through medium altitudes, reaching 3,100 feet per minute at optimal climb speed, but above 20,000 feet, climb rate decreased sharply. The P-51D, by contrast, maintained climb performance through high altitude due to its two-stage supercharger. At 25,000 feet, where the Zero was approaching its practical ceiling, the Mustang could still climb at 2,000 feet per minute and maintain level flight speeds exceeding 420 miles per hour. In a vertical zoom climb from high-speed cruise, the P-51D could reach 30,000 feet before losing momentum, while a Zero attempting the same maneuver would stall out below 25,000 feet. This altitude advantage meant American pilots could choose when and where to fight, engaging when conditions favored them and extending vertically when Japanese fighters attempted to force turning engagements. The tactical implications transformed Pacific air combat. Before the P-51DS deployment, American fighter pilots faced difficult choices: escort bombers and accept combat on Japanese terms at medium altitudes where enemy fighters had performance advantages, or patrol at high altitude and risk being unable to protect bombers under attack. The Mustang eliminated this dilemma. Pilots could cruise at 25,000 feet with fuel economy superior to low-altitude operations, dive to engage threats at any altitude, and zoom back to altitude with energy to spare. Japanese pilots, accustomed to American fighters that sacrificed altitude performance for other capabilities, found themselves outpositioned by an opponent that could match or exceed their climb rate through 20,000 feet and completely dominate above that altitude. Combat reports from Iwo Jima-based missions consistently noted that Japanese fighters, after initial engagement, would dive away and refuse further combat rather than continue fighting at altitudes where the P-51DS held insurmountable advantages. Yet for all its capabilities, the P-51D was not invulnerable. The liquid-cooled engine, while powerful and efficient, was vulnerable to battle damage. A single rifle caliber hit to the cooling system could cause catastrophic overheating within minutes. Japanese pilots learned to aim for the ventral radiator or the coolant lines visible along the fuselage sides. Zeros carrying 20mm cannons could shred a Mustang's thin skin with single bursts. The Mustang's light wing loading, beneficial for range and high-altitude performance, made it less stable as a gun platform than heavier fighters. And despite its superior speed and climb rate, the P-51D could not match the Zero's turn radius at combat speeds. Experienced Japanese pilots could still force overshoots if American pilots became fixated on targets and allowed speed to drop below 300 miles per hour. The key to Mustang success was energy management, maintaining speed above 350 miles per hour, using altitude advantage to control engagement geometry, and refusing to be drawn into slow-speed turning fights where Japanese maneuverability could compensate for performance deficits in other areas. The engineering evolution from Allison to Merlin engine installation illustrates how technological innovation compounds competitive advantages. The basic P-51 airframe, designed in 1940, represented excellent aerodynamic efficiency but nothing revolutionary. Laminar flow wings reduced drag modestly compared to conventional airfoils but did not fundamentally change aircraft performance. The real breakthrough came from understanding that supercharger technology determined combat effectiveness more than airframe refinement. An aircraft that could maintain power at altitude controlled the vertical dimension of combat, forcing opponents to fight at altitudes where they suffered performance penalties or refuse combat entirely. The Merlin's two-stage supercharger, developed through years of British research into compressor aerodynamics and intercooling systems, gave the P-51 an advantage that no amount of airframe optimization could match. This principle, that powerplant technology often matters more than airframe design, became fundamental to post-war fighter development. Jet engines would render the entire piston engine technology obsolete within years, not because jet-powered airframes were inherently superior but because jet propulsion eliminated altitude limitations completely. The human cost of the Mustang's development and deployment is measured not in lives lost but in lives saved through superior performance. Every bomber crew that returned from Germany because Mustang escorts drove off Luftwaffe fighters represented families spared grief. Every B-29 that reached Japan and returned to Iwo Jima without being shot down by interceptors was a crew that survived to fly again. The strategic bombing campaigns that the P-51 made possible remain controversial in their effectiveness and morality, but their impact on shortening the war by destroying Axis production capacity and forcing defensive fighter deployments is undeniable. The 8th Air Force lost 4,754 heavy bombers during the war. Without long-range escort fighters, losses would have been catastrophically higher, potentially forcing suspension of daylight bombing operations as occurred in late 1943 before P-51BS arrived in quantity. In the Pacific, the ability to escort B-29s to Japanese home islands allowed precision attacks on aircraft factories, oil refineries, and transportation networks that degraded Japan's ability to sustain military operations. The strategic impact of engine technology, specifically, the two-stage supercharger that made long-range high-altitude escort possible exceeded any single weapon system deployed during the war. The modification's legacy extends far beyond World War II. The P-51 remained in service with air forces worldwide into the 1980s, though in secondary roles. More significantly, the development process established principles that governed fighter design for decades. Integration of existing proven components from different sources became standard practice. The British Merlin engine in an American airframe, opposed initially by both countries' aviation establishments, demonstrated that optimal solutions often cross national boundaries and institutional preferences. The emphasis on range and endurance, initially considered less important than speed and climb rate, proved critical in both theaters and influenced post-war fighter requirements. The Air Force's F-15 Eagle and F-16 Fighting Falcon both incorporated fuel fraction designs that prioritized range, a direct legacy of lessons learned when short-range interceptors proved inadequate for escort missions. Even modern stealth fighters carry this DNA. The F-22 Raptor's internal fuel capacity and supercruise capability reflect understanding that controlling when and where combat occurs matters more than peak performance in isolated parameters. But the most profound impact was conceptual. The P-51's transformation from inadequate reconnaissance platform to war-winning escort fighter demonstrated that no aircraft design is permanently limited by its original specifications. The airframe existed as potential until the right power plant unlocked its capabilities. This understanding, that systems integration matters more than individual component excellence, became central to aerospace engineering. An aircraft is not the sum of its parts but the product of how those parts work together. The Mustang's aerodynamic efficiency remained constant whether powered by Allison or Merlin, but performance differed by 50% depending on which engine turned the propeller. Modern aircraft development obsesses over systems integration for exactly this reason. An airframe designed around one engine can be transformed by installing another, but only if the integration addresses cooling, structural loads, center of gravity, and the thousand other details that determine whether components work together synergistically or fight each other's limitations. The individuals who made the Mustang's transformation possible rarely received recognition proportional to their contributions. Edgar Schmew designed the airframe but did not choose the engine that made it legendary. Ronald Harker flew one test flight and wrote one report but changed the aircraft's destiny. The Packard engineers who adapted Rolls-Royce drawings to American production standards remain unnamed in most histories. Yet their collective achievement resonates through aviation history. They proved that solving the right problem, in this case, altitude performance rather than top speed or armament, could transform strategic possibilities. The B-17 and B-24 were excellent bombers, but they could not survive unescorted deep penetration missions against competent fighter opposition. The P-47 and P-38 were capable fighters, but their range and high-altitude performance had limits that prevented them from accompanying bombers to Berlin or Tokyo. The P-51D, with its Merlin engine and drop tanks, made strategic bombing viable by ensuring bombers could fight their way to distant targets and return. Whether that capability should have been used as extensively as it was remains a question for historians and ethicists. But that it could be used, that technology made possible strategic options previously impossible, demonstrates how engineering decisions ripple through military strategy and ultimately shape history's course. The story of the Mustang supercharger modification contains an irony that deserves attention. British engineers solved the high-altitude performance problem that limited American engine design, but British aircraft did not need the solution as desperately as American operations required it. Royal Air Force bombers operated at night, where fighter escort was impractical regardless of range or altitude capability. RAF fighters defended British airspace and provided cover for tactical operations but did not face the requirement to escort bombers on thousand-mile missions deep into enemy territory. The Americans, who needed long-range high-altitude escorts more than anyone, were building fighters around engines that could not provide those capabilities. The British, who had already developed the technology to solve the problem, were not using it in ways that fully exploited its potential. The confluence of British engineering, American production capacity, and operational requirements from both nations' strategic approaches created the P-51D and changed the war's trajectory. No single nation's approach would have achieved the same result. British production capacity could not have built Mustangs in sufficient numbers while maintaining Spitfire, Lancaster, and Halifax production. American engineering was years behind in supercharger development, focused on turbocharging solutions that worked for heavy bombers but proved impractical for single-engine fighters. The solution required cooperation across national boundaries, institutional barriers, and competing industrial priorities, a pattern that would repeat throughout the Cold War and continues in modern defense development. The technical details of two-stage supercharging, obscure to most people and boring to many, determined who controlled the sky over Germany and Japan in 1944 and 1945. Thermodynamics and mechanical engineering, compression ratios and intercooler efficiency, manifold pressure and critical altitude, these abstractions translated into life and death at 25,000 feet over hostile territory. A pilot who understood nothing about supercharger theory could feel its effects in the responsiveness of his throttle at altitude, the sustained climb rate that kept him above enemy fighters, the ability to chase down opponents who could not escape vertically. The Merlin's two-stage compressor was not magic, it was applied physics. But its effects seemed magical to pilots who had flown Allison-powered Mustangs and then transitioned to P-51DS. The difference between struggling to maintain altitude and having power to spare, between being forced to break off combat due to engine limitations and being able to press attacks until ammunition ran out, between surviving and dying because your engine could maintain power when the enemy's could not, these differences made the Merlin modification the most consequential engineering change applied to any American fighter during World War II. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world. The operational reality of flying very long-range missions from Iwo Jima tested both aircraft and pilots. Beyond anything experienced in the European theater. Takeoff from North Field required precision timing to get over 100 fighters airborne within minutes, forming up over the island before setting course for Japan. Each P-51D carried maximum internal fuel plus two 110-gallon drop tanks, bringing total fuel load to 489 gallons, nearly 3,000 pounds of gasoline that had to be burned down before combat maneuvering. The aircraft handled sluggishly when fully loaded, requiring careful attention to airspeed and climb gradient. Pilots climbed gradually to cruise altitude, burning fuel from the drop tanks first to reduce drag and improve handling while preserving internal fuel for the return flight and combat reserve. Navigation demanded constant vigilance. The first hour of flight carried the formation eastward over open ocean with no landmarks except occasional cloud formations and the slowly rising sun. Dead reckoning using compass heading, airspeed, and elapsed time provided the primary navigation method. Wind could push the formation off course by miles over a 3-hour flight, potentially causing fighters to miss the rendezvous with B-29s or arrive with insufficient fuel for the return leg. Lead navigators calculated wind drift by observing white caps on the ocean surface and comparing actual position against expected position using celestial navigation when weather permitted. Radio silence was mandatory until the formation neared Japan to avoid alerting coastal radar stations of the incoming raid. The tactical challenge began at the Japanese coast when early warning radar detected the incoming formations and scrambled interceptors. Japanese Army and Navy air units, though depleted by sustained combat losses and fuel shortages, retained experienced pilots flying a mix of aircraft types, A-6M0s, Ki-43 Oscars, Ki-44 Tojos, Ki-61 Tonys, and the formidable Ki-84 Frank. The Frank, introduced in mid-1944, represented Japan's response to American high-altitude bombers and represented a serious threat to P-51s. Powered by a 1,990 horsepower Nakajima Homar 18-cylinder radial engine, the Ki-84 could reach 388 miles per hour at 20,000 feet and climb to that altitude in less than 6 minutes. Its 420mm cannons and two 12.7mm machine guns carried enough firepower to destroy a B-29 with a single well-aimed burst. But the Frank shared the weakness of all Japanese fighters except the Zero, mediocre performance above 25,000 feet where thin air reduced the radial engine's power more severely than the Merlin's supercharged output. American escort pilots used this altitude advantage systematically, maintaining station at 27,000 to 30,000 feet while B-29s bombed from 25,000 feet, providing top cover that forced Japanese fighters to climb through the escort formation to reach the bombers. Any fighter that attempted this climb became vulnerable to diving attacks from above, and Japanese pilots learned quickly that accepting combat at disadvantageous altitude ratios led to losses they could not afford. The technical sophistication of the P-51's engine management system allowed pilots to optimize performance throughout the mission profile in ways impossible with earlier fighters. The two-speed supercharger drive shifted automatically based on altitude and throttle position, but pilots could override automatic operation when tactical situations demanded. Below 19,000 feet, low blower provided adequate boost with less parasitic power loss to the supercharger drive. Above 19,000 feet, high blower engaged, increasing supercharger speed to maintain manifold pressure as ambient air density decreased. The transition between blower speeds, if executed during high-G maneuvering, could cause momentary power loss, so experienced pilots learned to anticipate the shift and time it to occur during straight flight segments. The automatic boost control system adjusted throttle to maintain pilot-selected manifold pressure without exceeding engine limits, but pilots could override this system using the war emergency power setting that injected water-methanol mixture into the supercharger and allowed manifold pressure to increase to 67 inches of mercury, producing 1,790 horsepower for brief periods. This power level, sustainable for only 5 minutes before engine temperatures exceeded safe limits, provided critical performance during combat emergencies. Pilots activated war emergency power during zoom climbs to intercept high-flying interceptors, during breakaway maneuvers when jumping enemy fighters from above, and during final sprints to safety when damaged and pursued. The system's integration demonstrated the sophistication of American aviation engineering by 1944. A pilot did not need to understand the thermodynamics of compressor staging or the chemistry of water-methanol injection. He simply advanced the throttle past the detent and felt the surge of power that could mean the difference between completing the mission and becoming another loss statistic. Fuel management became the limiting factor on mission duration rather than enemy action. The standard VLR mission profile allocated fuel based on careful calculation. Climb to altitude consumed approximately 100 gallons, cruise to target at 25,000 feet burned roughly 0.70 gallons per minute, combat reserve required 100 gallons minimum, and the return flight consumed another 180 gallons including descent and landing pattern fuel. These numbers left almost no margin for extended combat, diversions due to weather, or headwinds stronger than forecast. Pilots monitored fuel quantity constantly using both mechanical gauges and elapsed time calculations. Running out of fuel over the Pacific meant either ditching in water that might be 60 degrees Fahrenheit, where survival time without rescue measured in minutes, or attempting an emergency landing on Iwo Jima's crowded runway with dozens of other aircraft also returning with minimal fuel. The island's single operational runway became a scene of controlled chaos during mass recoveries. Fighters landed at 30-second intervals, taxiing clear immediately to make room for the next arrival. Aircraft that suffered battle damage or mechanical failures received priority, but any hesitation or error could close the runway and force aircraft to ditch offshore. Rescue operations for ditched pilots were extensive, with destroyers, submarines, and patrol boats positioned along the return route specifically to recover pilots who could not make it back to base. Despite these precautions, dozens of pilots died not from enemy action but from fuel exhaustion and the unforgiving Pacific Ocean. The combat effectiveness of the P-51 in Pacific operations cannot be measured by simple kill-loss ratios. The primary mission was escort, and success meant allowing B-29s to bomb their targets and return to base without excessive losses. Japanese fighter tactics evolved to exploit any gap in escort coverage, attacking stragglers separated from formation or diving through the escort cordon to make single firing passes on bombers before escaping at high speed. The P-51 countered these tactics through disciplined formation flying and aggressive pursuit of any Japanese fighter that attempted to position for an attack run. American pilots did not need to destroy every interceptor, they needed to prevent interceptors from achieving firing position on the bombers. This defensive role required different skills than the offensive fighter sweeps that characterized European operations. Instead of seeking combat, escort pilots had to maintain position relative to the bomber formation while scanning continuously for threats from multiple altitudes and directions. Combat reports from Iwo Jima missions note that many sorties involved long periods of boredom punctuated by brief violent encounters when Japanese fighters attempted attacks. A pilot might fly 7 hours with only 2 minutes of actual combat, but those 2 minutes demanded absolute focus and instant reaction to threats developing faster than conscious thought could process. The psychological toll of these missions exceeded anything pilots experienced in European operations. A sortie over Germany typically lasted 3 to 4 hours, a mission from Iwo Jima required 7 hours or more. Oxygen masks worn for the entire flight at altitude caused facial numbness and headaches. Sitting in a cramped cockpit for 7 hours wearing a parachute, life vest, and survival gear caused muscle cramps and fatigue that degraded pilot performance during critical phases. The knowledge that ditching meant probable death from exposure added stress absent from European missions where pilots knew that landing behind enemy lines meant capture but likely survival. The cumulative effect of multiple VLR missions broke pilots psychologically as surely as intensive combat did. The standard tour for 7th Fighter Command pilots was 15 VLR missions, roughly 105 hours of flight time, after which pilots returned to the United States. This limit reflected recognition that human endurance had finite limits regardless of aircraft capability. Some pilots completed their tours without firing their guns in anger, others became aces within weeks. The randomness of combat meant that survival often depended more on chance than skill, a reality that eroded morale despite official emphasis on training and tactics. The maintenance burden for Pacific-based P-51s exceeded European operations due to environmental factors unique to Iwo Jima. Salt spray corroded aluminum skin and magnesium components. Volcanic ash contaminated engine oil and abraded cylinder walls. The island's primitive facilities lacked proper hangars, forcing maintenance to occur in the open regardless of weather. Spare parts arrived by ship on irregular schedules, creating shortages that required cannibalizing damaged aircraft to keep mission-ready fighters flying. Engine changes, normally a routine 24-hour evolution, could take days when hoists failed or replacement engines arrived damaged in transit. Ground crews worked around the clock to maintain sortie rates that doctrine required, often improvising repairs that would have been rejected as unsafe at stateside bases. The Packard Merlin, while reliable under normal conditions, proved sensitive to maintenance quality and operating procedures. Improper oil servicing could cause bearing failure within hours. Incorrect supercharger gear oil levels led to seized drives that destroyed engines. The glycol cooling system required careful monitoring for leaks that could cause rapid overheating. Each component demanded attention and expertise that ground crews provided despite exhaustion and inadequate facilities. The unsung story of the P-51's success involves thousands of mechanics who kept aircraft flying under conditions that would have grounded lesser machines and defeated less dedicated maintenance personnel. The strategic impact of Iwo Jima-based escort operations extended beyond protecting B-29s. The presence of long-range fighters over Japan forced the Japanese military to retain fighter units for homeland defense that could have been deployed to support ground forces defending Okinawa and other islands. Every fighter kept in Japan to counter B-29 raids was one fewer aircraft available to attack American ships supporting amphibious operations or to contest air superiority over ground combat zones. The Japanese could not ignore the bomber threat even though they knew that defending against escorted B-29s at 25,000 feet cost more in resources than the bombing raids inflicted in damage. This strategic dilemma, forced by the P-51's range and altitude capability, contributed to Japan's deteriorating military position as surely as did submarine warfare or amphibious operations. The Merlin engine's two-stage supercharger enabled an operational capability, very long-range escort at high altitude, that Japan could not effectively counter with existing resources and technology. The tactical imbalance created by this capability forced resource allocation decisions that weakened Japanese forces across all theaters. The evolution of American fighter tactics in the Pacific demonstrated how rapidly doctrine adapted when technology provided new capabilities. Early war tactics emphasized deflection shooting and gunnery skills, assuming that combat would occur at low altitude where Japanese maneuverability advantages forced American pilots to rely on superior diving speed and structural strength. The introduction of the P-51D with its high-altitude performance allowed American pilots to choose engagement altitudes and dictate combat geometry. New tactics emphasized altitude retention and energy management. Pilots learned to enter combat with speed advantage, make firing passes without losing altitude, and extend vertically when threatened rather than turning to defend. These boom and zoom tactics worked only because the Merlin engine maintained power through altitude ranges where Japanese fighters struggled. A Mustang pilot at 28,000 feet could dive on a Japanese formation at 22,000 feet, make firing passes through the enemy formation, and zoom back to original altitude before Japanese fighters could climb to counterattack. This tactic, impossible with Allison-powered fighters that lacked high-altitude performance, became standard procedure and minimized American losses while maximizing effectiveness against enemy formations. The contrast between early war Pacific combat, where American pilots often fought defensively using tactics designed to minimize disadvantages, and late war operations, where Americans held initiative and forced Japanese pilots to react to American attacks, illustrates how technology determined tactical possibilities as much as pilot skill or numerical superiority. The final months of the Pacific War saw diminishing Japanese resistance not from lack of will but from attrition that made effective defense impossible. B-29 raids, protected by P-51D escorts. Destroyed aircraft factories, oil refineries, and transportation infrastructure faster than Japan could repair damage. Pilot training programs, already degraded by fuel shortages and combat losses, could not replace experienced pilots lost in combat with escort fighters. Japanese aircraft production continued until the war's end, but new aircraft lacked fuel to fly training missions that would have prepared rookie pilots for combat. The Kyo-84 Frank, potentially competitive with the P-51D at medium altitudes, remained largely ineffective because pilots lacked experience to exploit its capabilities and fuel shortages prevented effective interception coordination. The strategic bombing campaign that the P-51D made possible did not force Japan's surrender directly, but it degraded industrial capacity and sapped military strength to the point where continued resistance became unsustainable. Whether Japan would have surrendered without atomic bombings remains debated, but clearly the conventional bombing campaign supported by long-range escorts reduced Japan's ability to defend its home islands and contributed to the decision-making calculus that led to surrender. The human dimension of the Mustang story involves not just combat pilots but the engineers, factory workers, and support personnel who created and sustained the capability. Packard Motor Car Company converted from luxury automobile production to aircraft engine manufacturing, training workers who had built transmissions and steering systems to assemble superchargers and maintain tolerances measured in thousandths of an inch. North American aviation's workforce grew from 4,000 in 1940 to 91,000 by 1944, including thousands of women who performed assembly tasks previously reserved for men. The social transformation of American industry, accelerated by war production demands, showed in the integration of minorities and women into skilled manufacturing roles. The quality of P-51D production, maintained despite rapid expansion and labor force turnover, testified to effective training programs and quality control systems that ensured engines and airframes met specifications despite being built by workers with minimal experience. The industrial achievement of producing 15,000 Mustangs between 1941 and 1945, along with 55,000 Packard Merlin engines, represents mobilization of human and material resources on a scale that could only occur during total war. The Mustang's success resulted not from individual genius but from systemic excellence across design, production, training, and operations. The comparison between the P-51DS development and Japanese fighter programs illustrates divergent approaches to technology and resource allocation. Japan developed capable fighters including the Kyo-84 Frank and J-2M Jack, both with performance competitive with American types in specific parameters. But Japanese industry could not produce these aircraft in quantities sufficient to counter American numerical superiority, and pilot training programs could not replace losses fast enough to maintain unit effectiveness. Japanese engineers understood supercharger technology and developed turbochargers for high-altitude applications, but production priorities and resource constraints prevented widespread deployment. The result was a technological gap that widened as the war progressed, with American fighters consistently receiving upgrades and improvements while Japanese aircraft remained static or regressed due to material shortages. The Mustang's transformation from Allison to Merlin power exemplifies American industrial flexibility and willingness to adopt foreign technology when it offered advantages. Japanese culture and industrial organization made similar adaptations difficult, contributing to technological stagnation that put Japanese pilots at increasing disadvantage despite individual courage and skill. The post-war influence of the P-51D extended into jet age development and shaped thinking about fighter requirements for decades. The Korean War saw Mustangs employed in ground attack roles against an enemy that had largely abandoned piston-engine fighters, demonstrating that the type retained utility even against jets for specific missions. The F-86 Sabre, America's primary Korean War fighter, incorporated lessons learned from P-51 operations, including emphasis on range, high-altitude capability, and systems integration. The Sabre's success against MiG-15s owed much to pilots who had flown Mustangs and understood energy management tactics developed in P-51D operations. Even modern fighters trace conceptual lineage to Mustang principles: the importance of range, the value of altitude advantage, the integration of proven components from multiple sources, and the recognition that systems work together to create capability greater than the sum of individual specifications. The F-15 Eagle's emphasis on thrust-to-weight ratio and sustained high-altitude performance echoes the Merlin Mustang's advantages over contemporary opposition. The understanding that controlling the vertical dimension of combat provides tactical advantages influenced fighter design through the Cold War and continues to shape requirements for fifth-generation aircraft. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world. The technical legacy of the Merlin Mustang combination extends beyond direct military applications into understanding how complex systems achieve performance through integration rather than individual component excellence. Modern aerospace engineering education uses the P-51 transformation as a case study in systems optimization. The aircraft had excellent aerodynamics but inadequate power at operationally relevant altitudes. Installing a superior engine was not simply a matter of bolting different hardware onto existing mounts. It required rethinking cooling systems, adjusting weight distribution, reconfiguring fuel systems, and modifying countless details that determined whether the components worked synergistically or fought each other's limitations. This integration challenge appears in every complex engineering project. Aircraft designers cannot optimize every component independently and expect superior overall performance. A lightweight engine that overheats under combat loads fails the system regardless of its power-to-weight ratio. A high-altitude supercharger that weighs so much it reduces climb rate at low altitude creates vulnerabilities even as it solves high-altitude problems. The Merlin installation in the Mustang succeeded because engineers understood these trade-offs and made design decisions that optimized the complete system rather than individual subsystems. The metallurgical challenges of building the Packard Merlin under wartime production constraints demonstrate American industrial capability adapting foreign designs to domestic manufacturing processes. Rolls-Royce Merlins used British standard alloys and production tolerances specified in imperial measurements that did not align precisely with American manufacturing practices. Packard engineers converted thousands of dimensions from British to American standards while maintaining interchangeability with Rolls-Royce parts for overseas operations where both manufacturers' engines might require service. The Supercharger impellers, machined from aluminum-copper alloy forgings, required specialized tooling to maintain aerodynamic contours that determined compression efficiency. Tolerances measured in thousandths of an inch had to be held across hundreds of parts while production rates increased from dozens to hundreds of engines monthly. The crankshaft, forged from heat-treated steel and precision-balanced for smooth operation at 3,000 revolutions per minute, weighed 140 pounds and required multiple machining operations using equipment that Packard purchased specifically for Merlin production. The connecting rods, made from drop-forged steel, were crack-tested using magnetic particle inspection to detect flaws invisible to visual examination. Quality control procedures that seem routine today were revolutionary in the 1940s when statistical process control and systematic defect analysis were nascent concepts. Packard's achievement in producing 55,000 engines with reliability equal to or exceeding Rolls-Royce originals demonstrated that American mass production methods could maintain precision traditionally associated with hand-fitted British assembly. The combat statistics from Pacific operations illuminate how technology translated into operational effectiveness. Between April and August 1945, 7th Fighter Command P-51DS flew 51 very long-range escort missions totaling approximately 5,400 sorties. These missions protected B-29 formations bombing Japanese industrial targets and resulted in claims of 124 Japanese aircraft destroyed in aerial combat for the loss of 23 P-51s, a 5-to-1 kill ratio that reflected both superior aircraft performance and pilot training. But these numbers understate the strategic impact because they measure only direct combat results, not the bombers that completed missions without losses due to escort presence. Statistical analysis from mission reports indicates that B-29 formations with P-51 escort suffered bomber losses 60% lower than equivalent missions without escort during the same period. The psychological effect on Japanese defenders further amplified this advantage. Japanese pilots learned that attacking heavily escorted formations invited losses they could not afford, leading to increasing reluctance to engage even when tactical situations appeared favorable. This erosion of Japanese will to contest American air operations resulted partly from material losses but equally from recognition that technological disadvantages made continued resistance futile. The fuel capacity modifications implemented for Pacific operations demonstrate engineering adaptation to operational requirements. Standard P-51D internal fuel consisted of 2 fuselage tanks totaling 184 gallons plus an 85-gallon tank behind the pilot seat, for 269 gallons total. This configuration provided adequate range for European operations where bomber targets rarely exceeded 400 miles from escort bases. Pacific distances demanded additional fuel, but simply adding tank capacity increased weight and reduced performance during the combat phase when maneuverability mattered most. The solution involved selective use of drop tanks that could be jettisoned when empty or before entering combat. 2 110-gallon drop tanks increased total fuel to 489 gallons, providing range exceeding 2,000 miles under optimal conditions. But these tanks created aerodynamic drag that reduced cruise speed and penalized climb performance when fully loaded. Pilots burned drop tank fuel first, maintaining internal fuel for the return flight and combat reserve, then jettisoned the empty tanks before engaging enemy fighters. This procedure required precise fuel management because internal fuel alone provided barely sufficient range for the return flight from Tokyo to Iwo Jima with minimal reserve. Mission planning calculated fuel burn rates for every phase. Climb to cruise altitude burned approximately 100 gallons, cruise to the Japanese coast consumed 130 gallons, combat operations might require 50 gallons depending on throttle settings used, and the return flight needed 180 gallons including descent and approach to Iwo Jima. These calculations left roughly 40 gallons reserve, enough for 20 minutes of flight time in a normal configuration or less than 10 minutes at combat power. Pilots who encountered stronger than forecast headwinds or who spent extended time at high power settings during combat often landed with fuel quantities below minimums that peacetime safety regulations would have considered acceptable. The maintenance challenges posed by sustained combat operations in harsh environments tested both aircraft durability and ground crew ingenuity. Salt corrosion affected aluminum skin, particularly around access panels and attachment points where dissimilar metals created galvanic couples that accelerated oxidation. Ground crews applied protective coatings, but constant exposure to salt-laden air required frequent inspection and touch-up to prevent structural degradation. Engine oil analysis revealed contamination from volcanic ash particles that entered the induction system despite filtration, causing accelerated cylinder bore wear that reduced compression and power output. Standard engine life between overhauls was 300 hours under normal conditions, but Iwo Jima engines often required removal after 150 hours due to environmental damage that maintenance could not prevent. Replacement engines arrived as complete assemblies that could be installed in 24 hours under ideal conditions, but ideal conditions rarely existed. Primitive hoisting equipment, exposure to weather during engine changes, and limited test facilities meant that many engine changes took multiple days and some installations required troubleshooting that delayed return to service. Aircraft availability rates at Iwo Jima averaged 65%, meaning that of 100 assigned aircraft, typically 35 were non-operational due to scheduled maintenance, battle damage repair, or parts shortages. Meeting sortie requirements demanded launching every mission-capable aircraft regardless of minor discrepancies that stateside operations would have grounded the aircraft for repairing. The evolution of pilot training to exploit P-51D capabilities reflected doctrinal changes forced by technological advances. Early war fighter pilot training emphasized aerobatics and dogfighting skills developed through extensive flight time building. Instinctive feel for aircraft handling. A pilot needed 200 to 300 hours before being considered combat ready. By 1944, training time decreased to 150 hours while producing pilots whose gunnery scores and combat effectiveness equaled earlier cohorts. The difference was systematic training focused on specific skills rather than general flying proficiency. New pilots learned energy management tactics explicitly, practicing boom and zoom attacks, vertical extensions, and defensive maneuvers that exploited the P-51D's high-altitude performance. Gunnery training used standardized approaches with deflection shooting taught through mathematical principles rather than intuitive feel. The K-14 gun sight, while not requiring pilots to understand its gyroscopic computing mechanism, did require training in proper pipper placement and trigger discipline that differed from earlier reflector sights. Ground school instruction emphasized fuel management, engine operation, and systems troubleshooting that prepared pilots for long-duration missions where mechanical problems might develop far from base. This shift from instinct-based to systematic training produced pilots who might lack the intuitive mastery of aircraft handling that characterized pre-war aviators but who could execute standardized tactics effectively and operate complex aircraft systems reliably. The democratization of aerial combat skill through systematic training rather than extensive experience represented a significant American advantage over Japanese pilot preparation, which continued to emphasize lengthy apprenticeship under experienced instructors, a system that worked well in peacetime but could not replace losses suffered during sustained combat. The strategic bombing debate that continues among historians and strategists finds one clear answer in the Mustang's role. Regardless of whether bombing won the war independently, escorts made strategic bombing operationally feasible and forced enemy resource allocations that weakened overall military capacity. German and Japanese fighters kept in homeland defense could not support ground forces fighting defensive campaigns. Industrial workers diverted to building interceptors could not produce tanks, ships, or other weapons needed at the front. The psychological impact of sustained bombing on civilian populations, whether justified or not, unquestionably affected morale and political decision-making. These effects required bombers to reach targets consistently and return in sufficient numbers that crews could complete combat tours rather than being ground down through unsustainable attrition. The P-51D's range and high-altitude performance made this possible. Without long-range escorts, strategic bombing doctrine might have been abandoned as losses exceeded acceptable limits. With escorts, bombing continued until enemy industrial capacity collapsed and strategic targets ceased to exist. Whether this capability should have been used as extensively as it was raises moral questions beyond technological assessment, but clearly the technology enabled strategic options that would not otherwise have existed. The comparison between P-51 development and contemporary Japanese fighter programs reveals divergent philosophies that influenced the war's outcome. Japan's A6M0, designed for maximum range and maneuverability at the expense of protection and firepower, reflected naval aviation doctrine emphasizing offensive fighter sweeps over defended targets. When combat shifted to defensive operations protecting Japanese-held territory from American attacks, the Zero's lack of armor and armament became critical weaknesses. Later Japanese fighters like the Keel-84 Frank and J-2M Jack addressed these deficiencies but arrived too late and in insufficient numbers to alter strategic balance. Japanese aviation industry produced approximately 35,000 fighters during the war, impressive but dwarfed by American production of 100,000 fighters of all types. Quality differences compounded this numerical imbalance. Japanese fighters relied on skilled pilots exploiting aircraft maneuverability to overcome firepower and protection deficiencies. American fighters emphasized systems that made average pilots effective, rugged construction that allowed pilots to survive mistakes, heavy armament that didn't require perfect shot placement, and performance advantages that let pilots dictate engagement terms. The result was predictable. Even when Japanese and American pilots had equal skill and experience, American technological advantages usually determined outcomes. As pilot quality declined through combat attrition, Japanese disadvantages became overwhelming. The Merlin Mustang's high-altitude performance exemplified this technological approach. It created an environment where Japanese fighters simply could not compete effectively regardless of pilot skill. The irony of British engine technology transforming an American fighter reflects the complex international nature of Allied cooperation during World War II. Britain, fighting for survival with limited industrial capacity, developed advanced supercharger technology but could not produce enough aircraft to fully exploit it. America, with vast industrial capacity, initially lagged in high-altitude engine development but could mass-produce aircraft once designs proved effective. Neither nation alone could have created the Merlin Mustang as quickly or in the quantities that changed the war's trajectory. British innovation combined with American production created synergy exceeding either nation's independent capability. This pattern repeated across Allied cooperation: British radar technology in American-built ships, American vehicles using British armor designs, combined research producing atomic weapons. The Axis powers, despite occasional technological cooperation between Germany and Japan, never achieved comparable integration. German and Japanese aviation industries developed independently, sometimes duplicating effort, often solving the same problems differently. The Allies' willingness to share technology, adapt foreign designs, and subordinate national pride to military effectiveness provided strategic advantages that supplemented material superiority and contributed to eventual victory. The human cost measured in lives saved through superior technology remains unquantifiable but significant. Every bomber crew that returned from Germany or Japan because escort fighters prevented interceptor attacks represented lives preserved. Every ground soldier who received effective close air support because fighters dominated the battlefield survived combat that might otherwise have killed him. Calculating the number of Allied lives saved by the P-51's capabilities requires counterfactual history that cannot be proven, but clearly superior aircraft reduced casualties among Allied forces even as it increased them among Axis militaries and civilian populations subjected to bombing. This asymmetry, uncomfortable to acknowledge, reflects the fundamental reality that technological advantage in warfare translates to battlefield success that kills more enemies and saves more friendly lives. Whether this justifies the development and use of superior weapons touches philosophical questions about war's nature and morality, but historically the incentive to develop technological advantages has driven military innovation for millennia. The Mustang's story ultimately demonstrates that transformative innovation often comes from unexpected combinations rather than revolutionary breakthroughs. The P-51 airframe was evolutionary, not revolutionary. The Merlin engine existed before the Mustang, but combining them created capability greater than either element suggested. This principle applies beyond aviation to any complex system where integration determines performance. Modern technology development increasingly recognizes that breakthrough capability comes from clever combination of existing components as often as from inventing new ones.